We can split up factors and multiples into 5 smaller bite-sized chunks. So we've got factor pairs, square and cube numbers, prime factor trees, lowest common multiple, and highest common factor. So if we look at factor pairs first, we're going to have, let's do an example. So let's start off with, say, 24. That's got quite a few factors. And all we're going to do is we're going to list out the pairs of numbers that times together to give us 24. So I know 1 times 24 gives me 24. I can do 2 times 12, or I can do 3 times 8, or I can do 4 times 6. And I can keep going, right? But what we'd see happening is I basically end up mirroring what I've just done, right? So I can keep increasing these numbers, but we actually end up with like a mirror line. And anything below that mirror line is just a repetition of what we've done previously. So these are really my 4 pairs, my factor pairs, that just numbers that times together to get the original number, in this case 24. Square and cube numbers. So square numbers are formed when we take a number and we times it by itself. So for example, 4 is going to be a square number, or I could do 5 times 5 and I could get 25. And again, 25 is therefore a square number because it's a number times itself gives us a square number. Cube numbers are very similar. In this case, we just times the number by itself 3 times. So 2 times 2 times 2 would give us 8. So 8 would be a cube number. And continuing on with this example, I could do 5 times 5 times 5, or 5 times 5 is 25, times 5 would give me 125. So these would be my cube numbers, and these would be my square numbers. Just examples of those two. I'm going to take prime factor trees over here. So prime factor trees are where we basically break down a number into smaller and smaller numbers until we can't break it down anymore. So for example, let's continue on with 24 as an example. So I split 24 up into 2 numbers, and normally we just pick 2 and something else. So in this case, it's going to be 2 times 12, because I know that 2 times 12 from my factor pair gives me 24. Well, I can't break up 2 into anything smaller, right? If I tried to do that, I'd get 2, 1, 2, 1, 2, 1, continuing on forever. So as soon as we get to a prime number that can't be split up anymore, that's the end of that branch. If you keep going with 12, I know 2 times 6 gives me 12. And I can split 6 up even further. I know 2 times 3 gives me 6. And I can work my way back up this tree, right? I know that 2 times 3 gives me 6. So I know that if I do 2 times 3, I get 6. And I know that 6 times 2 gives me 12. So this whole thing is 12. And I know that 12 times 2 must give me 24. So this whole thing gives me 24. And so I can times together my prime factors of a number, and I can get back to my original number. So I can always represent the original number as the product of its prime factors. Moving on, I'll go into more depth in a second with lowest common multiple and highest common factor. To stick with a nice example for now, we can use the prime factor trees to help us solve these, which we'll do in a second. But if I just pick a nicer example to prove the concept, let's pick 18 and 12. I'm going to find the lowest common multiple between 18 and 12. So one way of doing this, to kind of brute force it, is to just list out the multiples of 18 and 12. And I could keep doing this. I'd end up with 54, I think would be the next multiple, and so on. And with 12, I know I get 12, 24, 36, and 48, and again so on. And what we can see is we've got this common factor between both those two numbers. So 36 would be the common factor between 18 and 12. Moving on to the highest common factor. Again, if we look at this very briefly for now, I'll stick with the same example of 18 and 12. I'm trying to find the biggest number that goes into both 18 and 12. And so I could go back to my factor pairs topic, and I could look at the factor pairs of 18 and 12. Well, I know 1 times 18 is 18, 2 times 9 is 18, 3 times 6 is 18, I can't do 4, can't do 5, and then I get to 6, and I repeat what I've just done. Right, that's the mirror line there. And 12 is very similar. I do 1 times 12, or I can do 2 times 6, or I can do 3 times 4. And again, once I get to 4 times 3, I'm just repeating myself. Well, I know that if I look at these numbers, I'm trying to find the biggest number that they both share in these pairs, and I can spot here. I've got a 6 here and a 6 here. I've got a 9 and 18. There's no 9 in 12. I've got 12 in 12, but there's no 12 in 18. So 6 is the biggest number that they both share. But again, we'll see in a second how we can actually use the prime factor trees to tackle more complex versions of this topic. Right, let's dive into some exam style questions. So got a list of numbers, and we're going to write down a multiple of 6. So anything in the 6 times table, well, that's just going to be 12, if we know our 6 times tables. Factor of 15, so anything that goes into 15 a whole number of times. Well, I know 5 goes into 15 3 times, so that's going to be a factor of 15. And a square number, so a number that is formed when we multiply a smaller number by itself. Well, I know that 3 times 3 gives me 9, and 9 is in that list. So 9 is going to be my square number. Prime factor trees. So we'll do another quick example. This time we'll look at 72. So we're going to prep ourselves for the questions to come. So I can split this up into, say, 2 and 36, which in turn goes to 2 and 18, which in turn, I'm going to write a room, goes to 2 and 9, which in turn goes to 3 and 3. So I know that I can do 3 times 3 to get 9. I can then times that by 2, and that gives me 18. I can times this whole thing by 2, and that gives me 36. And I can times that whole thing, this whole result, by 2, and that gets me back to 72. So times that by 2 as well. So this whole thing would then give me 72. So that gives me 9. The next up gets me to 18. The next up gets me to 36. And the entire thing gives me 72. And we can be smart by this. We've got 3 times 3 and 2 times 2 times 2. So we could also write this as, well, I know 3 times 3 can be 3 squared, and 2 times 2 times 3 times 2 can be written as 2 cubed. Right, let's go on to the harder stuff. This is the highest common factor of 2 numbers. So again, I'm going to do my factor trees. You'll see why in a second for both these 2 numbers. Well, 60, I can split that into 30 and 2. Then I can go 15 and 2. Then I can do 5 and 3. And I can't split these up any further. So when I get to a prime, that's the end of the branch. Likewise with 1, 1, 4, if I split that into 2, that's going to give me 57. And I can then split that into, that's a multiple of 3. So I can split that into 3 and 19. And 19 is prime. So I know I've reached the end of all my branches. And what we're going to do now is we're going to look at the common factors between these 2 numbers. So, I've got a 2 here, I've got a 2 here and a 2 here, right? So I know 2 is a common factor of both these 2 numbers. Well, I could actually, before we do anything else, I can actually write down 60 as a product of its prime factors, just like we did above. I know 60 is just 2 times 2 times 5 times 3, right? If I just times all those prime factors together, doesn't matter which way around we do it. I'm actually going to, for the purposes of this, to show you what's going on, I'm going to swap those around, but again, it doesn't matter. And I know that 14 is 2 times 3 times 19. So 14 is just 2 times 3 times 19. Well, what I can see is I've got 2 times 3 appearing in both of my numbers, right? Which is 6. I know 6, therefore, goes into both my numbers. So whenever I've got a common pair of numbers, I know that I can times them together, and they'll then give me, I can times all my pairs together, and they'll then give me the highest common factor. So we don't have any other pairs, right? 19 doesn't pair with anything here. So we've only got that 2 pairing with that 2, and that 3 pairing with that 3. And so I know that I've got a 2 and a 3 occurring in both of these products of prime factors. Right, final question. finding the lowest common multiple between 70 and 50. So again, we're going to start off doing the prime factor trees. Again, you'll see why in a second. This is going to give me 7 and 10, and that in turn is going to give me 5 and 2. And because 7 is prime, that's the end of that branch. Likewise, 56, I can get 7 and 8, I can get 2 and 4, and I can get 2 and 2. So those are my prime factors that I can times together to get 56. Well, in this case, we're trying to find the lowest common multiple, right? And we can think of this as like a common multiple, just a common multiple, slightly weird M, common multiple is, for some reason I can't do M's today. A common multiple is going to be, a very lazy way of doing it. It's just 70 times 56, right? Because we know that 70 is going to go into it 56 times and 56 is going to go into it 70 times. Well, we also know that 70 can be written as 7 times 5 times 2. Or 5 times 2 times 7, whichever way we want to do this, right? I know 70 can be written as, I'm going to go 5 times 2 times 7. And I know that 56 can be written as 7 times 2 times 2 times 2. So I'm multiplying this, which is 70, by 56, which is 7 times 2 times 2 times 2. And that gives me 56. Well, what we can see is, we're getting this common multiple, but it's likely bigger than we need it, right? There's probably a smaller number that both 70 and 56 will also go into. And what we're going to do is we're going to try and spot where that redundancy is, where we're introducing more numbers than we need, right? And what we can see is, right, we've got a 7 in here, and we've got a 7 in here. But we can actually share 1 7 between these two numbers. And likewise, we've got a 2 here and a 2 here. But these two numbers can actually share just 1 2 between them. We don't need 2 2s. So what I'm going to do is I'm going to get rid of one of each pair. And if I rewrite this, I'm going to rewrite this over here. I'm going to have 5 times 7 times 2 times 2 times 2. So I'll get 5 times 7 times 2 times 2 times 2. And what we can see is we've still got 70 appearing, right? We've still got 70 appearing here, because I know that 5 times 7 times 2 must give me 70. And I've also got 56 appearing, right? I know that 7 times 2 times 2 times 2 is 56. So by getting rid of one of each pair, I've gotten rid of all the redundancy, and I've reduced this just general common multiple number down to the smallest common multiple. This is my LCM. And so we always get rid of one of the two pairs. You can think of that on the prime factor trees. I can identify my pairs. I've got, say, a 2 here and a 2 here. I get rid of one of those. And I've got, say, a 7 here and a 7 here. I get rid of one of those. And all I'm left with is 5 times 7, which is 5 times 7 times 2 times 2 times 2. And so that's how we could do it directly on our factor tree. We just cross out one of those, one of each pair. And that is the end of factors and multiples. I hope that was helpful.